Thanks for coming, everybody. My name's Fritz Klassner. I'm with the Office of Maunakea Management, part of University of Hawaii at Hilo. And this is our monthly Maunakea Speaker Series. Just before we introduce tonight's speaker, next month's presentation will be by Dr. Ken Hahn. He's a professor of geology and also the interim vice chancellor for academic affairs here at UH Hilo for at least a little while longer. But Dr. Hahn is going to talk about Maunakea, the growth and evolution of Maunakea as a volcano, sort of basis for the mountain as we know it. The Maunakea Speaker Series is actually a partnership between our office of Maunakea Management, the ELOA Astronomy Center, and the UH Hilo Physics and Astronomy Department. And we're always looking for more new ideas to talk about some various different and exciting work that's being done on Maunakea. So if anybody has suggestions on that end, let us know. And we interpret that broadly from sea level or even below sea level to the summit. But it's about the place. So with that, I wanted to introduce tonight's speaker. Dr. Stephen Businger is a professor of meteorology. Do you have an administrative role too? Should have read this. Are you?
I'm chair of the Atmospheric Sciences Department at UH.
Okay, sorry. Didn't have to have the speakers do their own introductions before long. So Dr. Businger is chair of the Atmospheric Department. It used to be called Nino. He also runs the Maunakea Weather Center, which provides, besides a twice daily forecast for the observatories in the summit of Mauna Kea, provides a lot of support and interaction with the National Weather Service. He's been doing research with our office on climate change and weather forecasting models and downscaling. Tonight's talk will be a little bit of a smorgasbord about past and future, present and future climate. But yeah, his interests ranges from Bob modeling and lightning to atmospheric seeing and transparency to climate change. So feel free to ask him questions. And with that, rather than listening to me, you came here to hear Dr. Businger. So I'm going to turn it over. Thank you, Steve.
No, thank you very much, Fritz, for that introduction. And thank you for turning down the lights a little bit. You know, there's some empty seats in the front here if you guys in the nosebleed section want to move down a little bit. So I do lots of different things. I study storm systems, hurricanes, coronal lows. I do weather modeling, a lot of weather modeling. And tonight, what I'm going to talk about is the Mauna Kea climate, past and future. And this is a little loop here that's taken at the summit of Mauna Kea to kind of show how interesting the clouds are that dance around up here during the daytime. But what I really want to do is talk about a whole range of different scales tonight, focusing first on the large scale, the big picture, like what controls the climate of Hawaii and the Big Island, and do our volcanoes control the climate in Hawaii? To what extent do they? Then I'll talk a little bit about changes of climate over the summit in the last 50 years or so, and what's going to happen in the future. And then just in closing, I'll say a couple words about thinking global and acting local. Because, as I say, I'm going to start from the big picture. So this is, you've probably heard that Cassini, the spacecraft that was launched by NASA to study Saturn, recently was crashed into the planet. And that is a picture of the Earth taken from Cassini, from Saturn, I should say, taken by Cassini from Saturn. And it always makes me think, you know, it's sort of that Carl Sagan moment where he said that pale blue dot that is our planet, that's where everything, everybody that we know, all the kings, all the presidents that have ever lived have been on that little blue dot. We live on a very tiny speck of dust in the universe. And I think that that's something to keep in mind when we're thinking about the amazing, Now it's not wanting to go forward. That's interesting.
So what did I do?
Well, I can do it with that.
Okay.
That's fine. Oh, now it's going a little too fast. So this is the planet Earth. I want to say a little bit about Earth, and because as you can see, the sun is shining and giving us a very nice full Earth at this particular moment in this image. And one of the things that you can notice is that there's an awful lot of blue coming out of the planet. There's also, it turns out, some red. And I wanted to explain that a little bit. The Earth's spectral signature, in other words, if you're looking at the Earth with a telescope, you can see that the color is a product of the planet's teeming life. And the life that I'm talking about is the plant life that is breathing out oxygen. And the oxygen and the ozone that is a product of the oxygen produces the blue color of the planet. Then we have also a lot of red light in the near infrared. The plants emit that red light. And so if you look at the spectrum, kind of in the visible, you get blue on one side, a lot of blue, and red on the other side, a lot of red. And that's a signature that we can look for on other planets to find life. And then we can worry about the climate on other planets. Another interesting thing is looking at the big picture. On last Friday, we had the equinox, the fall equinox. And that's a transition from fall to winter, or from summer to fall, rather, sorry. And it also is a time when the shadow of the Earth is exactly running north-south. And on one side, you've got 12 hours of daylight, and on the other side, you have 12 hours of night. And that's why it's called the equinox. During this time of year, you get 12 hours of each. Except at the poles, in the North Pole, we have sunset at the moment, and the South Pole, we have sunrise. Now, if you can imagine, one of the things that I wanted to put in this was a picture of the solar eclipse running across the country. My dad went to see it. He's 93. And he drove from a little island that he lives on north of Seattle down into Oregon to get right in the middle of this eclipse. And he had a thermometer with him, because I told him to. And he had his little glasses, and he was staring up at the sun, and he looked at the thermometer. The temperature in a 2-minute period of that eclipse, it dropped 10 degrees Fahrenheit. It went from 70 to 60 in 2 minutes. Now that's really sobering, because that means that our climate is incredibly finely tuned with regard to sunlight, which it is. And it turns out, if you look at this, this picture here, we have sunset taking place on the North Pole. So that's not just 2 minutes of darkness. That's 6 months of darkness. And that 6 months of darkness means a lot of radiation to space in the infrared, that's the wavelengths that the Earth radiates, and no sunlight to warm it up. So the pole is going to get cold, and it's going to be a polar winter as a result. And that affects our climate. It affects the birds too. And this again, you're probably wondering, what does this have to do with the climate of Hawaii? It's more looking at the bigger picture. I was looking at some radar imagery. This is Thursday night. Why am I looking at radar imagery in the Northwest Thursday night? Well, I thought, well, you know, it's the equinox. What are the birds thinking about this? And it turns out there was no rain. In the afternoon, there was absolutely no rain. So I knew that all the signal that was showing up here are birds, and they're migrating. And you can tell which direction they're migrating because the radar also measures the velocity. And you can see that there's incoming, is the cool colors are incoming to the radar, red colors are outgoing. So these birds are heading south. They know what's happening with the planet and the climate. They know that the sunset on the North Pole and that it's going to cool fast up there. The temperature gradient is going to start to produce winter storms, because that temperature gradient between the warmer air to the south and the cold polar air is what drives our winter storms. And so they're getting out of there, and they're going down to the southern hemisphere where things are a lot more quiescent. Now, there's one other thing that really drives our climate besides solar radiation, and that turns out to be water. Water is very critical for getting energy up to the poles and helping to mitigate this cooling that's taking place over the poles. And it also provides a tremendous amount of energy for storms, such as hurricanes, tornadoes, thunderstorms. So this is a giant cube that was on September 9th, was set down, and I told in Seattle, it was by a design company, and it was part of a design conference that they were having. So they put this ice cube down. It's really quite large, and I had my class estimate when the thing would be completely melted. And it turns out if you watch this, it's September 11th. Here's September 14th, September 16th, September 17th, and my students were, you know, like putting in dates. And all of a sudden, after September 17th, it really should have taken a few more days, but it disappeared, and I think somebody took it. And they put it in a very large vodka drink. So why am I showing this? The reason I'm showing this is that ice has a tremendous amount of energy in it that is required in order to melt it. And the energy that's involved is because of these hydrogen bonds. And I guess I won't go backwards to show that, but water is an asymmetric molecule, and two water molecules are super attracted to each other. And they form a very strong bond, and that's why ice takes so much energy to melt, because the water doesn't want to give up that bond, doesn't want to give up that energy. So it takes a lot of energy to melt water, and that has huge implications for our climate. Oops, I guess I am going through backwards. All right, so that same hydrogen bond that takes a lot of energy to melt takes even more energy, another order of magnitude more energy, in order to vaporize. In other words, if you have a liquid water liter in a pan and you want to boil that water away, you're going to take some time and you're going to take a lot of energy to do it. And if that water, it condenses again in a cloud, that heat comes back. And that's what drives hurricanes and tornadoes. It's the latent heat associated with water. Now, I mentioned the pole getting cold, and that is going to help drive the wind system of the planet. You get cold air up here, and sinking motion, very, very high pressure over the pole in the wintertime. And then further to the south over the oceans, you get this tremendous gradient, the temperature gradient. We call it a polar front, and you get all these storm systems. Meanwhile, close to the equator down here, you have the sun beating down, producing thunderstorms. And the sun thunderstorms cause rising motions, that's indicated here by the arrows, and sinking motion just to the north of Hawaii. And it drives this circulation. We call this a Hadley cell, with northeast trades over Hawaii. We have northeast trades in the summertime, 9 days out of 10. Now this is a global circulation animation showing water vapor. It's just showing the water vapor. And what you can see with this is that the water vapor is very much concentrated at low latitudes. This is all the water vapor associated with very high sea surface temperatures. The warmer the sea surface, the higher the vapor pressure you can produce in the air. The warmer, or I should say, the more humid the air will be, because we, as humans, we feel the relative humidity, not the absolute humidity. But it's absolute, very humid in this area around the equator. The little orange stripes that come up, though, that's precipitation, and it's we call them atmospheric rivers. And these atmospheric rivers, they come in and they intersect with the mountains, the coastal mountains in the US, and they produce a lot of flooding. in California, Oregon, Washington gets a lot of rain in the winter from these filaments that come up from the equator. But the equator is really where the action is, and it's the fuel for the hurricanes. But we live in the Hadley circulation. And so what we get is northeast trade winds, and this is on the side of, near Halipahaku, one of the cinder cones I'm standing up on top of, and I put my camera on a tripod and film this. And basically you have low clouds here beneath a trade wind inversion that are streaming from northeast to southwest. And if you look carefully up here, you can see the clouds are moving in the opposite direction. So that's that Hadley circulation that I showed before. It's actually a lot less, has a lot less vertical extent than it seems when I show that schematic. That schematic is very exaggerated in the vertical. So the atmosphere is just a pancake. It's very thin. And here we have the intertropical convergence zone, and this is where the northeast trades converge with the southwesterlies in the southern hemisphere, and that produces this line of thunderstorms down here. And Hawaii is right up in here, I think, right about there. Northeast trades coming down and meeting up with the southwesterlies and producing this zone of thunderstorms, which are prominent most of the year. As you can see, summer and winter, you have them south of Hawaii. But that same convergence, if you will, is associated with the Indian monsoon and the Australian monsoon in our wintertime. And so it's interesting. Now, it turns out that one of the biggest impacts on this larger scale on Hawaii's climate is something called ENSO, El Nino Southern Oscillation. And NOAA has put out a LaNina watch for this winter. And I wanted to say something about that. If you were, for example, the owner of a ski area and located up on Maunakea, admittedly, it's going to be a tough business. But this winter is going to be a better winter because there'll be more snow and cooler conditions, and there's going to be more rain in Hilo if this LaNina happens. Now, what is LaNina? This is actually from this month, September 6th. It's a sea surface temperature anomaly map. And what you can see is right around the equator, there's this huge zone of below normal temperature. It's the opposite of what you get in El Nino. This is a LaNina, which is cold on the equator. El Nino would be warm on the equator. And what it tends to do is it suppresses convection to the south of us, which kind of reduces the Hadley circulation a little bit. And let's take a look. So this is LaNina, and you can see that strong winds from the east on the equator. El Nino, you tend to almost get westerlies on the equator here, and much warmer temperatures and cooler temperatures in LaNina. So the difference is which direction is the wind blowing on the equator. And here's an animation where you can see the cold water upwelling forming here. And that's what the LaNina looks like, cold water. And it's because when you have strong winds from the east right on the equator, it causes divergence and it causes upwelling. So that brings the cold air, cold water from below. Well, so what does that do to the climate of the Big Island? So this winter, we are going to see LaNina conditions. If we do, then we're going to have more precipitation. These are monthly normalized climatological mean rainfall for 27 Hawaiian stations. So this winter looks like it'll be wet. If you had El Nino, you would be dry. You can see the difference. It's a huge difference. So this phenomenon of ocean sea surface temperatures, which are reacting to the winds, it has a big impact on Hawaii's weather in the wintertime. And how does it do that? It does it through impacting this jet stream, which runs around the globe. And so if you look at how these waves work. This is the jet stream. The jet stream is there because of the temperature difference between the pole and the equator. So this is very much associated with the fact that we got sunset on the pole, right? And so you end up with this wavy pattern, and the position of these waves, right? They're called Rossby waves, if you want to know, or planetary waves. The position of those waves depends, in a sense, on forcing from things like mountains and also El Nino, LaNina. So LaNina tends to have a certain effect, and let me show you what that effect is. Here's LaNina. Here's the Hawaiian Islands. It's a little hard to see them, but you tend to have a bit of a circulation, which is a conal low circulation over us with southerly winds, humid, rainy, not great tourist weather, but the plants love it. The other thing you get is northerly flow into the Pacific Northwest. So if you get tired of the rain here in Hilo, you just hop on a plane and go to Vancouver, and you'll have excellent skiing at Blackcomb, or whatever it's called up there, Whistler. Excellent skiing in the Northwest. In fact, you might even have some snow at sea level. It's going to be a cold winter for the Northwest. Warm and wet for us, kind of wet, maybe not warm, but stormy, a bit stormy, by which I mean we'll probably have 2 conal lows or more per month during the winter time, and one of those could maybe bring in some thunderstorms, and we can always hope. During El Nino, on the other hand, if I go back for a second here, during El Nino you get this ridge right over the Hawaiian Islands with almost no wind, high pressure, sinking motion, dry, dry, dry all winter long, and this is a El Nino situation. LaNina brings more rain, and so the lee side of the island is going to see rain, or hopefully, if LaNina happens. So I'm kind of excited about that. El Nino brings very large waves, which has its own set of problems. If you're a surfer, LaNina conditions don't really result in great surf. So that's a bit of a problem, a bit of a downside. But this is the forecast for LaNina, and it looks like it's going to be happening, a bit of a cooling. All right, so still looking at the big picture for a few more slides. I want to make the point that if you look at the temperatures over the US mainland, mostly in the summertime now, and from 1950 to 2012, this is what's happening. And it's actual data from the National Weather Service, the official recording sites that have been well calibrated. The sites that have seen a big change in the amount of urbanization have been excluded from this. And basically, it shows a large shift in the temperature distribution, with many more high temperature records being set as a result of global warming. Here's another way of looking at it. Starting from 1850, this is what the temperatures were, and as you go out from the middle, you're getting warmer temperatures. The 1.5 degree line is right there. Well, that's what the scientists say would be a good thing to try to stay below. And as you can see in February of 2016, we really showed an anomalous warm spike there. And this is global temperature now. The last was just the mainland US, but this is global temperatures. And they are sensitive to what's happening in the Pacific. When you have a big El Nino, it tends to cause the temperature to be a bit higher. And that's one of the reasons why you have that spike there. Where is that warming going? Actually, it's not going into the atmosphere for the most part. It's going into the ocean. And what's it doing? It's breaking the hydrogen bonds. What does that mean? It means that the water temperature is rising and that the water is expanding just a little bit. And we can see the impact of that sea level rise, in part because the water itself is expanding a little bit, and in part because we're melting glacial ice from Greenland and Antarctica and glaciers, and it's causing sea level to rise. In fact, Hawaii has seen some remarkably high sea levels this year, like almost a foot. And of course, we had a very big El Nino, and hurricanes are powered by latent heat. Latent heat, again, is that heat you get when water vapor molecules evaporate, and then it comes back when the clouds form and condensation takes place. And look at this summer of 2015 with that El Nino. We had all these hurricanes going by. And look at the Hawaiian Islands. We were lucky. This isn't some sort of magic that's preventing us from being hit by hurricanes. We were lucky. This is the hurricane tracks from 1949 to 1998. I need to update this. I did this way back. And you can see where the hurricane tracks are. Now, if you look at this last slide, there's an awful lot of hurricanes that are going this way and that are going close to the Hawaiian Islands. You remember in 2015 how many? We had one that hit the Big Island. In 2014, I think Gazelle. And then in 2015, we had a whole bunch of them roaring by, a lot of Category 4 hurricanes at once. And it turns out that back in 1871, there was a major Category 3 hurricane, might have been Category 4, that hit the Big Island. And how do we know this? We know this from Hawaii language newspapers. And we can actually track the time and the path of the storm, because hurricanes have eyes, right? And the eye wall is what hits and causes all the damage. And so we know from reports that it came through Waipio and it went over here to Lahaina and wiped Lahaina out. And we have lots of Hawaiian language newspapers. It's a really interesting, I think, cultural commentary that the Hawaiians were so quick to become literate and to start feeding the newspapers with accounts. And there's million pages of newspapers that are waiting to be translated, and there's a tremendous resource. And they've started a new center of Hawaiian language translation at the University of Hawaii in Mānoa. And this is one of the products that came out of it. So, sorry, let me go back. This is a study done from those past hurricanes, where the hurricanes went, and then doing a Monte Carlo kind of simulation to create more tracks, and it created this pattern. You can see that the main path of hurricanes runs just to the south of the Big Island. But what climate change is doing, and this is something which has been observed, and I don't have the slide for it, it's actually taking the hurricanes and moving them away from the equator a little bit. And so that's going to result in, according to one study of projected future hurricanes, a couple more hurricanes in the Hawaiian Islands per year than we have now. And that's in 2075. So that's an interesting, kind of a sobering thought when you look at what happened to Puerto Rico just now, and the Keys, and of course some of the Virgin Islands as well. If a big hurricane were to hit Hilo, well, I guess it could come in from the east. Yeah, it could really wipe Hilo right off the map, just about. So it's a sobering thought. What would be even well, if you're in Honolulu, that's the one that you worry about, is a big hurricane hitting Honolulu, because there's no infrastructure outside of Honolulu, no backup plan to kind of help the city get back on its feet. So it's a very interesting and sobering problem. So now I want to turn and talk a little bit more about local weather and and then some local climate change as well. So one of the things that this shows, this is a sea breeze front, And it turns out that there's not enough kinetic energy in the sea breeze in order for it to go up the slope more than just a little bit. And so the tops of the mountains tend to be pretty clear as a result. So what is a sea breeze? A sea breeze is basically where the trade winds are blocked by the volcanoes. And as a result, during the daytime, you get this return flow that's upslope. The mountain heats up, the warm air rises, and it gets pulled in from the ocean to be replaced, and that's a sea breeze circulation. At night, you have the opposite thing. You have cooling of the land, and you have a downslope flow. You can see in Hilo, it goes downslope at 2 in the morning, and then at 2 in the afternoon, it's upslope. So it's interesting. Every day, the mountain is breathing, right? It's breathing. So there's a huge impact on the weather in Hawaii. This is the summertime, 6 weeks in July and August. So summertime is particularly strong this way because the sun is intense. And this just kind of shows the warm air rising, and then you get this sea breeze circulation. And it cools, the beach. And then at night, you have the opposite with the high pressure developing over the land and going the other way. And of course, we have, in addition to that, we have the fact that the mountain itself is heating up and producing a mountain valley circulation. And this is Mauna Loa.